Hi everyone and welcome to the internet. So what we're going to be looking at today then is half-life. So hopefully by the end of this lesson you'll be able to explain what half-life is and also be able to carry out some of these calculations. Starts off then, we've got 3 questions on the screen. Have a go at answering those in your book for me. So I'm just going to give you a couple of minutes to get those answered. So let's do some marking then. For question 1, hopefully we had our periodic tables to hand so that we've got our uranium, 233 is the mass, 92 is the atomic number. Then obviously we form our alpha particle, so we've got our helium with the 4 and the 2, and then we just need to subtract those from our uranium, so that gives us 229 as the mass number and 90 as the atomic number, which if we look at the periodic table gives us thorium. For number 2, we shouldn't have seen a change in either mass number or atomic number because gamma is just an electromagnetic wave, remember. And then finally, for question 3, the mass number decreases by 4, give yourself a tick for that bit, and the atomic number decreases by 2. So add up your score, it'll be out of 4 for this one, so 1 mark for question 1, 1 mark for question 2, and the potential 2 marks for question 3. So give yourself a score out of 4 in your books. So what I'd like you to do then is to finish that sentence in your books. We did talk about this in our previous lesson on the alpha, beta and gamma radiation. So hopefully you can remember the name of the piece of equipment that we use to measure radiation. So finish off that sentence, get it written in your books. Just 30 seconds to do that. Hopefully the answer we wrote down is a Geiger counter. So give yourself a tick if you got that correct for me. If not, then obviously write it in now. Now, when we're talking about this radiation being emitted by radioactive substances, then this isn't something that is very ordered and sequential in how it occurs. What we actually find is that that radiation that's being emitted is emitted at random. So it's a case of we've got these unstable nuclei and they are going to emit radiation, but which one is going to emit at any given point in time, it's a completely random chance. Now, what we actually find then is that in order to measure the amount of radiation emitted, we use our Geiger counter, and we're going to record that as the radiation emitted each second. And what we refer to is something called the activity or the count rate. So wherever we're talking about the activity of a substance, we're actually talking about the amount of radiation emitted each second. And it's got a different unit, which is becquerels, which is given the symbol of a capital B lowercase q. So when we have 1 becquerel, what we have is 1 count per second. So I'm going to leave that up just for another minute and a half or so you've got a chance to write those points down for me. Question for you to have a go answering in your books then. If a material has an activity of 120 counts per minute, what is the count rate in becquerels? So I'll just give you a minute to have a go at doing that. Now, in this question, what we've got is a count per minute. So in becquerels, remember, that was the count per second. So hopefully we know that 120 would then be done in 60 seconds. So in order to convert that into becquerels, we've got to do 120 divided by 60, which gives us an answer of 2 becquerels. Give yourself a tick if you got that right. Now, the title of today's lesson, half-life, we need to understand what that actually means. And it's quite simple, it's quite self-explanatory in a lot of ways. Because when we're talking about half-life, we're talking about the time taken for the activity to halve. We could also phrase that in a slightly different way and say it's the time taken for the nuclei of half of the atoms to decay. But the key thing here is that the activity is reducing by half. So make sure you've got those written down as our definitions. I'll leave those up for about another minute. Let's actually look at this in a nice, easy to understand, hopefully anyway, diagram form. So if we look at the picture on the far left of your screen to start off with, the green ones are the radioactive atoms. And if you count them up, you'll find that there are 12 radioactive atoms at the start. So that would be our activity of 12. Then, one half-life later, we've reduced that by half. So that means from 12 we go down to 6, and you can see there are only 6 green atoms there. And if we have another half-life pass, then we'd be down to just 3 radioactive atoms. So each half-life that passes, the number of radioactive atoms, or the count or the activity, that has reduced by 50%. So it's gone down by half. When we're talking about the half-life of different radioactive materials, then it's not a case of everything has the same half-life. Some of them can be really long, and some of them can be incredibly short. So half-life varies depending on the isotope we're looking at. And in the table there, I've just given you some examples. You don't have to memorize these for an exam, just to give you the idea of the difference we can experience in half-life. So if we have a look at the top one there, helium-6 has an incredibly short half-life of just 0.8 seconds. So what that tells us is that if we've got a sample of helium-6, then the count is going to decrease by half every 0.8 seconds. If we look at radon-222, then that's got a half-life, a bit longer this time, of 3.8 days. So that means the activity reduces by half every 3.8 days. Carbon-14, much longer this time. We're talking about half-life of 5,700 years. And carbon-14, because it's got this nice long half-life, is actually really quite useful to us when we want to carry out a process called carbon dating. So that's where we've got very old remains of things like potentially mummies and so forth, or items from the distant past that we've dug out of the ground. And what we can do is, by working out the amount of carbon-14 still left, we can then work out how long ago that thing died. So very clever. And then the last one on there, uranium-238, this has a little bit longer half-life of 4.5 billion years. So we can see there from 0.8 seconds to 4.5 billion years, we've got quite a range of half-lives depending on the isotope we've got. So we know what half-life is, and we now need to know how we could actually use this in different kinds of calculations. Now, one of the things we could be asked to do is to calculate half-life from a graph. So we've got a graph on the screen here, and they'd ask you a question along the lines of, work out the half-life for this substance. Okay, so let's have a little look to see how we actually use one of these graphs in order to work out the half-life of a material. So the first thing we need to do is look at the total activity we start with. So that's where the line starts on the far left hand side. So at time 0 we need to know what the activity is. So what we can see here is there's 400 and here's 500. And if we count, we've actually got 10 squares between 400 and 500. So each of these squares is worth 10. And if we count up, we can see that we've got 8 squares going up. So that means that this point here, our initial activity is 480. So hopefully we remember a half-life is how long it takes for half of the radioactive nuclei to decay or for the activity to be halved. So what we need to do is 480 divided by 2, and that gives us 240. So what we need to do then is on our graph we need to find 240. So 210, 20, 30, 40. And then we're going to use a ruler to draw a line across to the curve itself. Obviously you will use a ruler for this in the exam. Then what we do is we come down from that line all the way down again with a ruler to our x-axis, and we're going to read that off. So again we've got 10 squares between 10 and 20, and in this case there's 2 there, so that means it is 12. So we have a half-life of 12 days. And that's it. So that's how we actually work out how long a half-life is from the graph. There's a second way that they could also ask us to work out half-life, and this is through calculation. So the kind of question we could get is on the screen here for us. A sample of radon-222 has an activity of 100 becquerels. It has a half-life of 3.8 days. Calculate the activity after 11.4 days. So I'd suggest you jot down that example question first of all. I'll leave that up for about a minute for you. Okay, so in order to work out this one then, our sample of radon-222 has an activity of 100 becquerels, it has a half-life of 3.8 days, calculate the activity after 11.4 days. So the first thing we need to do is work out how many half-lives it has been through. So we're told in our question that we're looking at it after 11.4 days and it's got a half-life of 3.8 days. So the first thing we need to do is 11.4 divided by 3.8, and if we put that into our calculator we're going to come out and find that that is 3 half-lives. So this has experienced 3 half-lives. What we then need to do is calculate the new activity. So hopefully we remember that each half-life is reducing it by half. So we can do a half times a half times a half. So that's our 3 half-lives. And if we know our maths, then that means it is an 1/8. Then all we need to do to work out our new activity is an 1/8 times by 100, which gives us a nice answer of 12.5. and that is becquerels. So that's it. Now, some of you may not be a great fan of fractions, in which case there is another way we can do this. So again, we start the same way because we've still got 11.4 days and a half-life of 3.8. So we need to know how many half-lives. So 11.4 divided by 3.8 still gives us 3 half-lives. Then what we're going to do is work out what the new activity is. So if you're not a fan of fractions, you can always do it as 100 divided by 2 will give us 50. So that's 1 half-life. Then we can do 50 divided by 2 gives us 25, second half-life. And then 25 divided by 2 is going to give us 12.5. So that's our third half-life and therefore our final answer. So 2 different ways that you can do it. Obviously you can use the fractions if you're confident with those. If not, you can just divide by 2 however many times you need to based on the half-lives. Okay, your turn to have a go at a couple of questions. So 2 questions on the screen. See if you can answer those in your books. So I'll give you about 4 minutes to have a go at that. Okay, let's check these answers then. So carbon-14 has a half-life of 5,700 years, so that's an important point for us. It will have initial activity of 1,000 becquerels, and what will the activity be after 17,100 years? So first thing to do is work out the number of half-lives, so that's 17,100 divided by 5,700, and that will give us 3. Then what we need to do is obviously work out half times a half times a half, which gives us an eighth. And then to work out the activity is just an eighth times by 1,000, which gives us 125 becquerels. So if you got that right, give yourself a mark. Okay, so carbon-14 has a half-life of 5,700 years. It has an initial activity of 6,000. How long will it take for the activity to be 375? So one way we can do this, and there are more than one way you can do this, but one way that we could do this is to do the reverse of what we've done. So 375 times 2 would give us 750. Then we can do 750 times 2 is 1,500. 1,500 times 2 gives us 3,000, and then 3,000 times 2 gives us 6,000. So that's our initial count again. So then we can just count up, so that's going to be 1, 2, 3, 4. So the answer then is 4 half-lives. But we're not done yet, because remember it asked us how long it was going to take. So we know it's 4 half-lives, and we know each half-life is 5,700, so we need to do 4 times 5,700, which is, just give me a second to use my calculator, 22,800. So 22,800, and don't forget the units, years. So one way you can do it, obviously there are other ways, but just to show you one solution. So last thing for today then is to have a go at our plenary questions. So you've got up to grade 5 is the column on the left. Those of you with target grades of over a grade 5, it's the column on the right. So I'll leave this up for a couple of minutes so you can have a go. But obviously if you think you'll need longer, then just hit pause on the video. As always, you can find the answers to the plenary over on my website, sciencewright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.